Now that we understand sampling distributions, we can investigate confidence intervals. We're going to first consider confidence intervals for the population mean. So let me motivate this by looking at an example. Are we getting fatter? So according to the CDC, the average weight for American men in 1960 was 166.1 pounds. We want to know the average weight of men today and if it's higher. So how could we do this? Well, we could take a random sample of several U.S. men, in this case 125 U.S. men, and we could find that mean weight, and let's say it turned out to be 195.4. So we could conclude that men today weigh an average of 195.4 pounds. That's something that we call a point estimate. So it's a single number that estimates our population parameter. Or we could use an interval of values around that 195.4 to estimate the weight today. And we could conclude that men weigh 195.4 pounds with some margin of error, so plus or minus a certain number. So again, this first method of estimating, that's what's called a point estimate. So a point estimate is a single number that's going to estimate our population parameter. The second method is what's called an interval estimate, which is going to be a formula that uses our sample data, and it's going to find an interval that estimates that target parameter. And it's going to have the form of the point estimate plus or minus a margin of error. So what we need to find out is, how do we get that margin of error? Well, we first have to specify what's called a confidence level. So how confident are we going to be of our estimate? Now, the way that they write this is they use the symbol alpha, and 1 minus alpha is a decimal, like 0.90, and then we multiply it by 100, so we would get 90%. So this 1 minus alpha times 100 is just a 2-digit percentage, something between 0% and 100%. And what that does is that confidence level, that represents the proportion of intervals that we would expect to contain that population parameter, in this case population mean, if a large number of different samples were chosen. And now the researcher usually picks that confidence level. So how does the sampling distribution fit into this process? Well, the sampling distribution of our statistic is actually going to be used to determine that margin of error for our estimate. So let's remember the properties of our sampling distribution of X bar, the sample mean. That sampling distribution of X bar is going to be approximately normal if either the population is normal or n is greater than or equal to 30. So if you got a normal population, the sampling distribution will be normal for all sample sizes. If the population, the parent distribution, is not normal, then as long as n is greater than or equal to 30, the sampling distribution will be normal. The mean of the sampling distribution, mu sub X bar, is equal to the mean of the population. And the standard deviation of the X bar distribution, the sampling distribution, is the standard deviation of the population divided by the square root of the sample size. So that's specifying the variability in our sample statistic. So for purposes of this example, let's pick a 95% confidence level. So that's our value for 1 minus alpha times 100. So in this case, alpha is actually 0.05. It's a proportion. So we want to know what z-scores would mark the middle 95% of the data on a normal distribution. So we've got 95% of the data in the middle, 2.5% out here, 2.5% out here. We want to know those z-scores. So we're given percentages, we want z-scores. So this is an inverse norm problem. So z is going to be the inverse norm. And then remember, you put the area to the left of the z-value. So for example, this z-value's got 95 plus 2.5, 97.5%, so 0.975. So inverse norm 0.975, so 9.75 to the left. So let's go ahead and compute that. So second variables, inverse norm is number 3, and 0.975. Come down and paste that. 1.9599, 1.96. So this is about 1.96. So that's saying that this value down here is 1.96, and this one over here is going to be the negative of that, negative 1.96. So 95% of the data is going to be between z equals negative 1.96 and z equals positive 1.96 if the data is normally distributed. Okay, that's for any normal distribution. Well, since the sampling distribution here is approximately normal, that means that 95% of this will be actually the sample data. In this case, it's not proportions, but it's means. 95% of the sample means will be between 1.96 negative and 1.96 positive. That is, they're going to lie within 1.96 standard errors or standard deviations of the mean. So with the sampling distribution, a lot of times I'll call the standard deviation the standard error. So here's a picture of what we've got going on. This is our sampling distribution. So that's the histogram of the means of repeated samples. And 95% of all of those sample means are going to be in the middle here between the mean plus 1.96 standard deviations for this distribution, sigma x bar, and mean minus 1.96 standard deviations, sigma x bar. So that means 2.5% of the sample means out here and 2.5% of the sample means out there past those cutoffs. So what that's saying, if 95% of all those sample means are in the middle here, that's saying that for 95% of the sample means, x bar values, they're going to satisfy that x bar, that sample mean, is between those two cutoffs, mean minus 1.96 standard deviations and mean plus 1.96 standard deviations for our sampling distribution. Well, you can algebraically rearrange this and get the following. X bar minus 1.96 standard deviations on the sampling distribution is less than equal mu, that's the population mean, is less than equal 1.96 x bar plus 1.96 standard deviations on the sampling distribution. So what's that inequality saying? That's saying that for 95% here, for 95% of the sample means, that mu, the actual population mean, is within 1.96 standard deviations of that x bar value. Okay, so that happens 95% of the time. So if you form this interval around x bar plus or minus 1.96 standard deviations, that's going to contain the population mean 95% of the time. That's what a confidence interval is. So that 95% confidence, again, is saying, hey, here's our sampling distribution, mean in the middle, and mean minus 1.96 standard deviations, mean plus 1.96 standard deviations. So now if you take a sample mean, x1 bar, and then you add and subtract 1.96 standard deviations to that, notice that this population mean is inside that interval around x1 bar. So let's say you take another sample and say that the x2 bar, and that falls outside of this range here. Well, that means that when you add and subtract 1.96 standard deviations to that, then the population mean now is outside that interval. So your population mean is either going to be inside the interval you get from your random sample, or it's going to be outside the interval. So, well, it should be inside that interval 95% of the time. That's what that 95% confidence level means. Let's illustrate this by looking at a simulation. So here I've got, this is my population mean mu, which in this case is 0 for this simulation. I've generated one interval here. So I'm going to resample. So that's another interval. And notice that the population mean is inside that interval. It's inside, this is the interval here, the line. And I resample. And I get this is another interval, and I notice that the mean's inside that interval. Well, that's just one at a time. Let's go ahead and do 100 different intervals. So here's 100 different samples and 100 different intervals of 1.96 standard deviations around them. And the ones that are colored in red, those are the ones where the population mean's not in that interval. Well, this is a 95% confidence interval simulation. We've got 2 intervals that don't contain the population mean, and that means 100 minus 2, 98 that do. Well, let's resample, pick 100 different samples, and now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's saying 10 samples that don't contain the mean, those are the red ones, and 90 that do. So let's resample again. Now we've got 1, 2, 3, 4, 5, 6, 7 that don't contain the mean. That means 93 that do. Okay, resample again. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 that don't, and 90 that do. And if we keep this process up, we keep doing this, on average, we should have 95% of those intervals that are the gray and only 5% that are the red. So here we've got 1, 2, 3, 4, 5, 6, 7, 8. So notice it varies because there's variation in samples. But we keep on sampling here, keep on sampling, keep on sampling. You notice that some of them, like this one, 1, 2, 3, 4, have less than 5 red intervals, and some have more than 5. But on average, we'll have 5 red intervals. So that means 5 intervals that don't contain the population mean, and 95 that do. That's what that 95% means. 95% of the intervals will contain the population mean.